Hello, everyone. Are we ready to start, Vlada?
I am.
Okay, perfect.
But I was waiting for some kid. No, we're not waiting anymore, right? So we're starting.
That's fine. We will probably have 10 today, so that's fine.
Okay, so let us start. Hello, everybody. Let me keep my camera off just in case, so the connection would be stable, right? So today, let me share my screen. Where did it go? Where did it go? Just a second, some technical issue. I can definitely see it on my screen. Right, here we go. Yeah, so today, this would be a short webinar due to some unexpected reasons we have. It would be mostly about function analysis, and we'll focus on asymptotes. So let me start with a simple example, and probably all of you already know how to deal with that. So this is a function, and I'd like to know what are the asymptotes, and I needed to sketch it. So I want to somehow sketch this function to analyze what is it, what is the form of this function. Can I see the chat? Yeah, I can. So I'd like you to somehow communicate with me. So maybe some ideas of where I should start. Oops, I'm sorry. There was something. Yeah, so vertical asymptote. Yeah, of course, first of all, we can state that x equals to 1 is certainly a vertical asymptote. It's the value which our function doesn't get any values at all, yeah, where it's undefined. Can't divide by 0, yeah, just the same. Okay, so let me try and sketch it. Sorry for the picture, it might not be very perfect, but we'll just try and our best here. So yeah, this would be my vertical asymptote. It passes through the point 1 on the x-axis. Okay, yeah, and somebody is already mentioning the oblique asymptote, the slant asymptote. And this someone proposed that probably it is y equals to x. Well, let us see. What is the best way for us to understand what is our slant asymptote here? Any guesses, any ideas? Okay, let me show you something. So yeah, so we have some polynomial divided by another polynomial. Let us use this and actually divide those polynomials. So we will get some quotient and some residue. We can do using different methods. One of the methods is to adjust the numerator so it looks exactly like my denominator multiplied by something. So for instance, here I can subtract x and add x. Then I have plus 1, which just stays, divided by x minus 1. Right, why do I need this? Well, from here, I can just see that this will lead me, sorry, this is a little bit clashing. So this will give me just x plus 1 divided by x minus 1. So pretty much like y over y equals to x, but not exactly because we still have something to do because this one can be divided as well. So what do we have here? Let me adjust it somehow. Let me move your chat box somewhere else. So that would be x plus x minus 1, and I need to add 2. Does it make sense? Do you understand what I'm doing? Just give me some feedback. Yeah, okay. If not, give me this feedback as well and ask me questions. Okay, so that's what I'm doing. And again, I divide x minus 1 by x minus 1, and I get x plus 1 plus 2 over x minus 1. Now, why is it enough for us to define the slant asymptote? Because basically, this is the core of our function, so to say, because as x goes to infinity, plus or minus, this number, this value goes to a 0, right? So basically, we start dealing with the line. And again, I'm sorry, it doesn't look very nice. So this is x plus 1. So sort of, these are our boundaries. Our function is somewhere here. And one of the easiest ways to understand where it is to actually substitute some value. For example, I can substitute value, what was it? For example, 2, what would it be? It would be 5 over 1. So definitely it's greater than value 3 here. So that leads me to the idea that my function is somehow squeezed in between those two lines, but in this particular part. And here, how do I know how it behaves here? Well, first of all, let me understand how it intersects anything. So we can see that we never get y equal to 0 as our numerator is always a positive number and denominator, well, it's a denominator. So the only intercept we can get here is the intercept with the y-axis, right? How do we get it? As usual, we put x equals to 0 into the formula, and we get 1 over minus 1, which leaves us with y equals to minus 1. So my other part of the function, other branch, is here. Now, why am I so sure that it behaves like this? Well, as these are asymptotes, my branches should come closer and closer to this particular line. And that's how I basically know how it should look like, at least how the sketch looks like, right? So definitely that's not the whole analysis of our function here. And you know that to find these particular points, we would need to find the derivative of a function and to explore its zeros and to explore probably the second derivative, or one can just use the first derivative and explore its pluses and minuses to see whether our function increases or decreases. So to establish whether this turning point is a maximum or a minimum. But we won't do it now because as I said, it would be a short session, and also I have a few more tricks to show to you. Okay, fine. So now let's move to the next example, which would be pretty much the same. I just wanted to show to you how we usually can apply this particular method to some other rational functions. So imagine you have something like this. In this particular case, it's not very convenient to use just the same method, right? Because it would be a little bit, well, too many efforts, and you need to actually watch what are the coefficients here, too many steps. So rather than that, I should remind you that you can always divide a polynomial by another polynomial using this, in Britain system, it's bus stop method. In other systems, you would see in other methods, but rather, just the same. Let's try and do that. Let me just give you an answer here. You can do it in your books, and I will give you an answer just because I'm not very good at this bus stop notation, and I don't want to mislead you here. Basically, I was taught a different method, so I will just give you the result. So the result would be x cubed is 2x squared plus 3 multiplied, and this is my quotient, by x over 2, and my residual is minus 3x over 2. Right, so what does it give to me? Basically, it gives to me what is my slant asymptote, what is my residue, and as I can see, the residue always should be the polynomial of a lesser power than the one we used in the denominator. This is very important because if it's of the same power or bigger, you should continue your division, right? But here it's just this, and we can see that as x tends to infinity, this goes to the 0. And again, this is how I found my slant asymptote here. Okay, so now let us move to my third example. Any questions so far? No. Okay. So my third example would be about square roots. And that's a nice one. And that's where we will stay a little bit longer. So here we go. Imagine you have square root of the power 3 of the function x cubed minus 2. That's an interesting function because why does it have any asymptotes? Does it have any asymptotes? How do we know it? How do we learn it? Well, the interesting thing is that it does have an asymptote, which is not very, it's not evident, right? So let's see how we can define it, how we can find it. First of all, we have no vertical asymptotes because this function is defined for every x. If we would have a vertical asymptote as we had it here, we would have some loop there, right? But we don't. So we only need to look for some slant asymptote. You had a definition, which was in your assignment, which looked like this. So the slant asymptote is an asymptote if this condition is true, right? When x tends to plus or minus infinity, well, usually we just look at plus infinity, and usually it's the same for minus infinity. So let me show you another approach which can be more handy, sort of, which you can use, because that means you should guess both numbers at once and sort of, you know, using try and error, find this slant asymptote, which is quite, you know, time consuming. So let me show you another way. If we have a slant asymptote, this condition is true. Why is that? Well, we can easily show it from here, because if we have some slant asymptote and this condition is true, that means that f of x is actually mx plus n plus some small value at each point. Imagine it's epsilon. Let us name it epsilon. We can also construct a function epsilon of x, showing that this is infinitely small values. The values of this function are infinitely small, and other than that, our function is somewhere around this line, right? But if I substitute it here, let's look at what is here. I will get mx plus n plus some small epsilon divided by x, which is m, plus constant, plus this epsilon, which can vary, but still it's very, very small. So all in all, it's just 0 or something around 0, and the limit is m. I know that's not a very, you know, strict proof, but for our purposes, it's fine. So why do I introduce you with this approach? Because basically that's what we'll try and use here. So I have this function. Now I divide it by x, and I try to figure out what's my limit if my x goes to infinity. What can I do about that? Any ideas of how I should approach? Anyone? Oh, Taylor expansion. I think it's too much. Let us just move x from yeah, let's cube x and put it inside the cubical root. So that would be lim cubical root x cubed minus 2 divided by x cubed. Now, let me simplify it. So that would be 1 minus 2 divided by x cubed. Where does it go when my x goes to infinity? What's the limit? 1, exactly. Exactly 1. So now I know that my gradient of my slant asymptote is just 1, but I still don't know this n. Another good way of looking at this particular definition, now we know how to find a gradient, but also now we can use this gradient and say that the free term, the y-intercept, if we're looking at the y-intercept form, right? So our n is just the limit of the following expression, f of x minus mx, when we know this m. This can be easily seen from here. As n is my constant, I can just take it out of this limit because it's a constant number, a constant value. It doesn't actually influence this limit, right? We can just take it out and move to the right. And that's how we will see that the limit of such an expression is just n. So as we've split this definition, we now can use those two ways of finding our coefficients. So let us move here. What do we know? We know that my m is 1. We know that my function is, again, cubical root x cubed minus 2 divided by x and minus x, right? So this would be a little bit, you know, we have to do something about that. Well, first of all, let's use the common denominator, right? What would it be? What would it be? Oh, no. Sorry, no, sorry. That's not the function, right? Because the initial function was this one, sorry. We don't have to divide it by x. I look at it and I'm a little bit bewildered. What's going on? Yeah, sure. The original function was just cubical root of x cubed minus 2. Sorry, my mistake. Yeah, and to deal with that, we use quite a common approach. So once we're dealing with roots, we usually multiply by, so to say, conjugate expression. What does it mean? Well, when it's a square root, it's a conjugate expression. Remember how we did it, like, for example, square root of a minus, I don't know, square root of b. If we multiply it by square root of a plus square root of b, which can be named conjugate because this minus and this plus are just opposite signs, we will get a minus b. So we get rid of square roots, right? For the cubical root, it's a little bit different, and we will use another formula. Let me remind it to you. I'll start it from here. So imagine you have the difference between two cubes. Who remembers how can we factorize this expression? Any ideas? Does anyone remember? If not, yeah. Thank you so much. Thank you. Oh, a lot of you actually remember. Yeah, of course. So we can use it x minus y, x squared plus xy plus y squared, an incomplete square here. So that's what I use here. I would multiply by an expression which is aligned with this expression here. What would it be in this particular case? Let's see. So this is my x here, and this is my y here. So let me see. That would be, let me move back to the black ink. So that's x cubed minus 2 cubical root minus x. Then I multiplied by the square of this x cubed minus 2 plus the product x cubed minus 2 and plus x squared. And at the same time, I divide by this same expression, which is actually non-zero. And you can easily check that this never can be zero or even negative, right? So that's my expression here. Let me, oh, why did I put x cubed here? Why doesn't anybody tell me that it's just x? I don't know why it's cubed. Okay, x cubed minus 2, too many cubes, I suppose, and x squared. Yeah. Why did I do that? Wasn't it a cube? Yeah, it was. Sorry, it's not that important, but yeah, let us be more precise here. Yeah, sure. Nothing changed here. It's just me missing some signs, some some numbers. Okay, so what do we get on top? Something nice looking at, hope. We get this thing cubed minus x cubed. So what would it be? X cubed minus 2. Yeah, right. Minus x cubed. That's why we started all this. And here we have this kind of nasty expression, which will just, we'll put as some dots here because we do remember what it is. But on top, we just get minus 2 divided by this particular thing. Now, what happens if I send my x to infinity? Where does it go? X is very, very, very big. I think it goes to infinity. Yeah, of course. So this thing goes to infinity, meaning that the whole fraction goes to 0. And that means that actually my slant asymptote is just y equals to x. Now, let me just show you the picture of this function, if you don't believe me. Here, how it behaves. So this is my cubical root of x cubed. Let me sign it here. So that's x cubed minus 2 cubical root, the red one. And the blue one is just y equals to x. It's kind of bewildering, but you can check. There are many. You can construct your own just to check how it works. Quite impressive. I don't know. I find it impressive. I mean, you never know that such a function would even have some asymptote. Okay. These were some easy examples. we were basically playing around the definition you had, or just dealing with rational functions when we can sort of see the slant asymptote from the formula itself. But now let's move to a different problem where we will need some quite new approach. We will talk about L'Hopital rule. And I know you haven't done it before. I'll show you why it works and when it can be, when it can be useful for us in terms of asymptotes of some functions. We'll look at a function which is not very good looking, a little bit scary. So where do I start? Imagine we need to analyze this function. Well, first of all, and usually that's where we start, we'll start with whether it's an odd or even function. We didn't mind with the previous function, because basically, we saw there neither. But here, it would be quite handy because we'll see that some points, we'll just check our answers, whether it's symmetrical or not, because obviously, what is this function? Let us check what happens if I substitute minus x inside. Well, I get minus x e to the power of minus x squared. So just minus f of x. So this is an odd function. And we will only use it for the benefit of this symmetry, just for that. Okay. It is a continuous function on real numbers. And that means, again, that we have no vertical asymptotes. But what about slant asymptotes? What happens with this function? What about horizontal asymptotes? Do we know anything about this function? So what I'll do here is I'll try to look at how this function behaves if I put my x to the infinity. Well, as we said, this is not an odd function, so we'll only deal with plus infinity, because for minus infinity would be just the same but symmetrical, right? So let me rewrite this function as this. Basically, I'm dealing with the limit of such a function when my x goes to plus infinity. So what do I do? What can I do about that? How can I look at this limit? Here, I will introduce you a L'Hopital. Bottom goes, actually, bottom doesn't go to 0. Bottom goes to infinity, and top goes to infinity. Yeah, so that's the problem here, right? So they both go to infinity, and we don't know how it ends. So what about the ratio, right? Because it can vary. So let me introduce you this L'Hopital. That's a French mathematician. I heard some rumors that he didn't actually prove this L'Hopital rule, but just bought the rights from Bernoulli. But maybe that's, that's a mathematical joke or something. Just a story. So what is our L'Hopital rule and what does it tell us? Let me move to a different color because it's a little bit separate chapter today. So L'Hopital rule is used for such cases where we look at the ratio of two functions. Do you take the derivative? Yeah, exactly. Somebody already knows what we do. So it usually can be applied when we have this sort of case where both functions tend to 0 or both functions tend to infinity. So in this case, we don't know what would be their ratio, and we cannot understand how to deal with them. So in this case, we will use a L'Hopital rule, which is exactly this. The limit of such a ratio, as x goes to infinity, is the limit of the derivative of this function. Well, of course, if we have these derivatives, if they can be defined, etc., let's not dwell on that right now. Let's just look at it, when everything is fine. Imagine everything is already fine, everything is already defined, but usually, of course, you should always check that you actually can apply this rule. We'll start from the case when we have a zero limit, okay? So we even can start from the place because it's not very, basically it doesn't matter where we put our x, and let us put it to a, so some constant here. And I know that the proof I will show you will sort of ignore the case when we go to infinity, but I just want to show you that actually you can apply this rule and using some more math, prove it for each case you actually need. So I will only show you how it can be seen that it works. It actually works and it can be applied. Imagine you have two functions and f of a is 0 and g of a is 0. Just like simple proof of this L'Hopital rule for some specific cases from where you can see that it actually works. So this is what we're given. And we need to understand what would be the limit of this ratio if we move closer to this point where both functions are 0. Again, as I said, it usually is used in these two cases. Okay, so first trick, let us not change anything, but just say that I subtract 0 from top and from bottom. I don't change anything. Then I notice that this is exactly my f of a and g of a. Okay, so f of x minus f of a over g of x minus g of a. Does anybody feel where I'm moving with that? How does it relate to the derivative? Any ideas? Yeah, we sort of try to come to the differentiation from first principles. And to do that, to make it more clear, let us divide both numerator and denominator by x minus a. But not only, here we would use the property of limits where we can split it as the limit of the top thing over the limit of the bottom thing. Again, as I said, normally each mathematician would ask you some dull questions about why do you make this step, why you are allowed to do so, etc., etc. But here, let us be a little bit more physical-like. You see, it works. Let's just continue and see how it will end up. But actually, you already see how it will end up. So what do we get here on top? What is this? By definition, yeah, exactly. By definition, it's just f prime of a, minded. And here, just the same, but for g, j prime of a. And that's it. The only thing I want to show to you, another thing I want to show to you is how we can use this L'Hopital rule when we deal with functions going to 0 for functions going to infinity. So actually, it's, probably some of you will see where I go with this, but imagine that those functions go not to 0, but to infinity, approaching when x is approaching a. So what do we do in this case? Well, we will flip them. So that would be 1 over j of x on top and 1 over f of x on the bottom instead of this expression. Please check that it's exactly the same, right? And now, as we know this rule already, that would be just the same as the limit of their derivatives. Please don't take the derivative from the denominator only. We have to do the whole thing with the derivative of a reciprocal function. So what do we have here? We'll get j prime over j squared. Let me skip x's, right? F prime over f squared and limit here. And let me rearrange it. So that would be, just let me check with my notes. Yeah, so j prime over f prime. Oh, sorry, I don't have No, I have limits. Yeah, okay. And f squared by g squared. Again, using all the properties for the limits, I can rearrange it so you can see that I can divide by f over g. So, and divided by j prime f prime. So yeah, let me just rewrite this left-hand side here so you can see what I actually do here. So that was the limit of f over j. We started with that. And now we came to this limit of such a thing. So from here, you can obviously see that that means that lim of f divided by g is actually lim of f prime divided by g prime, because we can rearrange it all to both sides and put it in a way we need it to be. Or, you can leave it as j prime over f prime, which doesn't actually change the whole thing dramatically, but still it's better to leave it this way because we started from here. So now you can see that this rule is actually, I would say, as as usually I do some very strict proofs, I would say kind of works. Well, we need to be very precise about our wording, about what we do here, but basically it works. And that's why we can use it. And that's where we will use it and see how it works for us. So let me come back to the black ink, let me come back to the function I had. Okay, so we're looking at the limit of x approaching infinity of a function x over e to the power of x squared. Knowing L'Hopital rule, let us differentiate both functions. What do we get? What do we get? Yeah, 1 on top. On the bottom, it's 2x times e to the power of x squared. Okay, now, can we see what happens if x approaches, well, approaches not the right word, but yeah, approaches infinity? What happens with this limit? Yeah, it goes to zero. Obviously, it goes to zero. And here, it can be seen just, at once. Here, actually, we could have started looking at it in terms of, let's look at Taylor series. We could have seen it without derivatives, but I do believe that with derivatives, it's a little bit easier. And from now on, I think you can just use this trick whenever you need it. So what do we know from here? Well, we know that as x goes to plus infinity or to minus infinity for the same matter, our function approaches zero. So it's something looking like what I draw here, but not exactly. Well, let's look at this function now in terms of our everyday analysis. So where did we start? It was an odd function. We know its behavior, but we'll come to this later. Well, let us look on the derivative, on the first derivative. What would be the first derivative of this function? Please don't confuse. The derivatives here are taken from the numerator and denominator separately. It's not the same as the derivative of the ratio of two functions, right? That's different. But here we have x e to the power minus x squared again, and we need to take this derivative. So can anybody help me here? And please simplify it. If you found it, simplify it so we can actually see what are the zeros, for example. While you're trying to figure it out, I'll start by just developing it. Oh yeah, somebody's already, okay, so that would be first function prime, which is 1, second function untouched, oops, what was it? Yeah. Then plus first function stays as it is, and we take the derivative of this one, which is a chain rule, so I get e to the power of minus x squared multiplied by minus 2x, right? And here, and that's a very, shouldn't be on, never mind. Okay, I don't mind. So, okay, there was our multiplication rule, and inside we had a chain rule, okay? So here, I would advise to you to factor out e to the power of minus x squared. So we're left with 1 minus 2, oh, sorry, was it 2x? I think it was 2x. Oh, sure, it was x, yeah, x squared, yeah. Minus 2x squared. Okay, and this is our first derivative. And when is it equal to 0? Of course, this particular factor never can be 0. So when we look at these brackets, and this gives us plus or minus 1 over square root of 2 as turning points. Or, some points where our derivative is equal to 0, but there are two different approaches here. You can take the second derivative if you like and we actually needed to find the inflection points. But as I'm an old school, usually I look at this derivative in terms of what are my zeros, what are my positive and negative values of my first derivative, so I can easily see how my function should sort of behave. So let me do just it. You can do it any way you like. I just show my approach. You can use it or not. So what is my approach? I look at the line, a numerical line. I have this 0 point. And let me now explore. If I take x bigger than this value, then the value in the brackets is actually negative, right? Is it? Is it? No, just give me a second. No. Sorry. Did I get one minus somewhere? I do feel that I have to. Oh yeah, probably I made a mistake. Yes, I think I made a mistake last time. Yeah, because it should be negative, right? The closer it's to, so when it's in between those points, the closer it's to 0, it's positive, and then it's negative again. Please check after me, but I think that's pretty much the case, and I think I made a mistake in my notes. So what does it mean? It means that, first of all, that was an increasing function, then was decreasing function, then was increasing function, and then it was decreasing function again, which means that this point was a local maximum point, this one was a local minimum point. And that's what I expect from my function, something like this. And also I know some behavior on its end. Okay, but that's not enough. Let's do the whole thing. We still have some time. I was so keen to give you everything. I was in a bit of a rush in the beginning. So let us take the second derivative from here. Let me give you a chance to explore it yourself. Well, basically, it's just pretty much the same. We split it with the multiple rule, right? So that's first, well, we can do it any way around, but let's say with first one is differentiated, then times second one stays, plus e to the power minus x squared, and then we differentiate this one, which leaves us with minus 4x, right? Right. And again, factor out this particular function, e to the power of minus x squared. Basically, we can look at it as if it's just some number because it's a positive value for each x. So it behaves as if it's 5 or 7 or any other coefficient you have here. And you're only dealing with those. And actually, I can do what I can do. I can factor out minus 2x as well, right? So I'm left with, I think I should have had 3 at some point. So let me see, maybe I'm. So what I'm left with 1 minus 2x squared minus No, plus 2, right? Right. Oh, here goes my 3. 2x e to the power and 3 minus 2x squared. Let me make a small stop here. Can you see how I got there? Do you have any questions? Anything at all? Any questions, guys? Or everything is clear and you understand what I'm doing and why I'm doing it? All good. Okay, only one message. Oh, 2 messages. I think that's kind of a statistics here. Okay, so this is my second derivative, and I always need it, as you may know, for my inflection point. So where do I expect my inflection point? 1 here, x equals to 0, and 2 here, where x is equal to plus or minus square root of 3 over 2, right? Right. And again, you see what I can check here. Why is it square here, by the way? I know that my function is an odd function. So basically, I'm looking for this symmetry. And as I get this symmetry, I may understand that it aligns with the whole function, right? I didn't make any mistakes so far, so everything is good. So, okay, what happens here? What's going on with the concavity of this function, right? Why do we need those points? Because we need the concavity. So I have 0, square root of 3 over 2, square root of 3 over 2 with the negative sign. And what I have plus here, right? Right, because this is a negative and this is a negative. Then minus, then plus, and then minus again. And the last thing I want to do is just to show you the picture of this function and maybe just put it here so we can see that it fits. And here we go. Let me just, did I? Yeah, well, now you can see that this picture, oops. Does it work? No, it didn't work. Let me try again. Yeah, here we go. Let me move it a little bit up so we can see that everything is okay. Well, let's start from the beginning, I believe. So from the beginning, what we have, remember how I sketched the behavior around the first derivative 0 points. And we can see that it's just the same, right? It goes down, up, and down. Remember how we knew that we have a horizontal asymptote, because what does it mean that approaching infinity, we approach 0? This is our horizontal asymptote. And here we go, here it is. It is an odd function, and we can see it from the picture. And now those points here, which are stop points, they reflect what? Well, basically these stop points never reflect something. These green points reflect our inflection points, right? So this is our 0, where we change our concavity. This is our square root of 3 over 2. And this is our minus square root 3 over 2. So I believe we've nailed it. And the picture just the same that we were expecting it to be. Okay. Okay. Do you have any questions? I think that's pretty much it. I've prepared 4 examples for you. Let me briefly go through them again, just in case. So first 2 were mainly about how we deal with polynomials. Once we have a polynomial on top and on the bottom, we can just divide one by another and sort of find the slant asymptote as it is. After that, we need to understand how the function behaves because basically it's squeezed in between those lines, but it can be of this way, like I draw it in blue, or like I had it in black. And one of the simplest way to check which way around is just to substitute a value and understand in which part of this plane you actually sit. Then we dealt with cubical roots, and we played around the definition of an asymptote, of a slant asymptote. We rewrote it we split it in 2 different cases. First, how to find the gradient in a more easy way, and then how to find the free term, right? The y-intercept using this gradient. And the last bit was about L'Hopital rule. We tried to have a look at how basically we would prove it. Why is it true at all? We saw that, yeah, it's connected. We can prove it for some specific cases. Basically, the proof was around x approaching some specific value a. We never discussed infinity, but we sort of made it legal and use it from now on. So we applied it to this particular not very good looking function because it helped us to understand how it behaves on infinity. And all together with all the function analysis that we already know, we managed to sketch the graph. And yeah, if you have time, could you go over how domain and ranges work in composite functions, especially if there are domain restrictions in one or both functions to be okay. I hope I understand the question correctly. Do I have time? Yeah, I have a few minutes. Okay, so basically what you need to know, once you're dealing with a function, which is, for example, a ratio of two other functions, that's it. This is your new function. And when you're talking about domain and range, you're looking at this particular expression. Can you get it from the previous two? Well, you can, and some even, sorry, it's again a little bit, some even do it this way. They can draw the top function, then they can draw the denominator function and sort of try to understand their behavior by dividing each point by each point. So that would be something like this. So where do we get a trouble? Well, of course, we get a trouble when I get the value which is 0. So here at first of all, I see that here I will have a loop, right? I will have an asymptote because that's my 0. So that's where I start. But other than that, well, what you can see from here, well, first function doesn't give you any specific domain restrictions because its domain was the whole real numbers line. But its range was from 0 to infinity, which now is not exactly the case because, you know, this number can be negative. So it can reverse each positive value we had to -1. And that's why we basically have to look at where we get, whether we can get a value at a point 2, and the answer is no. And that's where we'll get a different one. And what happens when we approach these two? Well, of course, when we approach 2, when we come closer to a 0 value. And if we divide something by 0, it goes to infinity, right? And that's what we have here. We can divide one function by another as we had it previously. So I would add and subtract, rather subtract and add 2 terms, which will help me to see what's going on here. So that's x plus 2x over x minus 2, or you can just divide one polynomial by another polynomial, it's up to you. So basically it's x plus 2 plus, let me just put it as something here. So yeah. So now I would know that this is my slant asymptote, and I will try and squeeze my function inside it. So answering your question, yeah, you definitely can link the domains and ranges of two functions you were given with their ratio. But basically what you do, you look at the points where your denominator function gives you 0 values, because these are the most important ones. You will try and explore what happens around this point, because as you can see, something goes to infinity. And that's pretty much it. I think that's the only advice I can give you from top of my head, right? Yeah, because in general, what I do, I always explore it all together, and because, you know, too many different cases, what can happen with the functions, as we've seen. For example, whether they have a slant asymptote or not. This one has. If you have just 1 over x minus 2. No, if you have if you have x over x minus 2, you will have a horizontal one. I'm not sure that I answered your question, but I do hope I need to consider the main restriction for both functions in the result. Well, basically, you need to consider the range sort of the range of the second function, the one in the denominator, would be a restriction now, because it can be 0, and this is our restriction, right? You certainly have to look at both. Yeah, of course, if some functions are not defined from the beginning, yeah, for example, you had, and that's a tricky one actually, because it depends on how you approached it. Because of course you can somehow rewrite this expression so it will start with a function with a different domain and range. For example, one of the examples here, what happens if we take a square root of x squared? Well, of course it should be just absolute value of x, right? But in some particular cases, if you restrict your domains, you can just say that it's just x if you restrict your domain to positive numbers. So it's a little bit tricky. You should always consider all the information you have, and the domain and ranges is the most tricky part of it, because sometimes that's where everything is damaged, because you have a very tricky domain, because at some points it's undefined, not because it's undefined as you see it on the formula, but just because it was undefined from the beginning for some specific reasons. For example, it came from a ratio of 2 different functions, and now it has a different form. That's how it can happen. So I'm sorry, I'm not sure that I have answered it, and I didn't have enough time for that, but I do hope that I made it a little bit clear. Okay, no worries. So I guess that's it then. Thank you so much. I hope it was helpful. I especially hope that L'Hopital rule would be useful for you for some, problems, not only in function analysis, but mostly, here you applied a lot. So thank you. Let me stop sharing. Let me maybe start my video for a while just to say hello to you all. And see you some other time. Okay. Thank you. It was nice to have this webinar with you. Thanks. Bye. Bye-bye.